Okay, we've made it through to session 7 of the meeting, and we have 5 speakers in this afternoon session, the middle 3 of whom are students. You can see from the asterisks on their names. And this is going to be a nice circling around through the ice sheets, above, below. It's a really nice combination of talks, which are being pulled up as we speak. So I can go ahead and introduce the first speaker, who is an invited speaker. It's Brent Minchew, and he's going to be talking about closing the frequency gap between remote sensing and in-situ observations. So this has a lot of tie-ins to the last session.
Yeah, great. Thank you very much. Thanks everybody for hanging out, and for those of you who are joining us virtually, thank you very much to the organizers for the invitation to give this talk. And yeah, it is rather well timed, given the conversation that just went on in the last panel discussion, talking about drones, what we can do with drones coming forward in the near future, what sort of observations can we make, how can these things help propel us forward. So that's effectively what I am talking about in this talk. These are some kind of new ideas, some things that have started to come together over the past few years. I'm going to give you some of the details that we have available, but it'd be great if you're interested in this kind of thing, that we can chat either during the discussion after this or offline while we're all hanging out. So co-authors deserve a ton of credit for this. In many cases, what I'm talking about is pulling together a lot of pieces that have been worked on by a number of individuals over time, and starting to bring these things together and starting to focus on forwarding the science and making better observations so that we can learn more about the processes in WAIS and other areas. Can I just make this full screen, or can we just go ahead with this? Good with that? All right. Okay, so I figured I would start this off by just taking a paraphrasing quote from one of the luminaries of WAIS that is usually here, not here this year, but Sridhar Anandakrishnan has talked for a long time and quite a bit and done a lot of work, I think, to move the field forward in understanding the frequency response of glaciers, ice streams, ice sheets, and so forth. So I've heard him talk about this a number of times. He's done a lot of work on this, and I think that this is a really powerful idea that gets us started and connects with what we're doing. Frequency response, if you don't know, very powerful concept, and understanding dynamical systems, it's simply the response of a given system to forcing of a variety of frequencies. All right, so we want to be able to observe the ice sheet with frequencies as high as what Seth was talking about earlier with the seismometers, all the way down to the lowest frequencies that we tend to get from satellite observations long term, all the way out to paleo records and so forth. And so the talk is really about trying to close this frequency gap that generally exists in our observations. So kind of 2 main types of observations that we have. Satellite observations that give us all kinds of useful information. I'm interested in glacier dynamics, so we get surface velocities, strain rates, things of this nature, shown up in the top left, an image that many of you are familiar with at this point in time. So satellites are flying over. They're great for giving us broad spatial coverage. We've gotten to the point that we have data downlinks that allow us to have relatively fine spatial resolutions of order a few meters, maybe out to a few tens of meters, depending on the instrument. But one of the main drawbacks to satellite observations is they tend to give us relatively crude temporal resolution. They're kind of limited by the repeat time of the satellites, or by the number of satellites that we can put up and take advantage of in a particular constellation. So temporal resolution of satellites typically sort of days to years and so forth. And so we can get great information from that, but not everything that we necessarily want to know. On the other end of the spectrum, stuff like what Seth does, a number of other folks do, looking at seismometers, in-situ observations, GPS stations, and so forth. These are really great for giving us high temporal resolution, but of course they're limited in their spatial coverage and resolution. They're generally instruments that are put in a particular place and give us point measurements in space. And between these things, there's this whole frequency gap, with frequencies that range from kind of tidal frequencies to multi-daily frequencies and so forth, and this is this gap that we want to start to fill to get really detailed information on what's going on. So our motivation in thinking about observational technology is that we want to make progress in understanding some key physical processes, right? Calving and rifting, sliding at the bed, rheology of ice, and so on and so forth. But in order to do that, in many cases, we need observations that give us broad spatial coverage, that give us high spatial resolution, give us high temporal resolution, and then have a number of other features connected with the specific process that we're looking at. And in the future, I'll argue that we might be able to have these observations using aircraft, and specifically uninhabited aerial vehicles. So, or high altitude, in this case, long endurance drones, so hail drones. So what we're going to talk about is two basic concepts, some collaborations that we spooled up within MIT to think about how we solve the technical issues related to this problem. And there are two main concepts kind of in-member cases that we're pushing forward on to try to get a sense of which one works. Each of these are going to have their own advantages and disadvantages. First one we're talking about, this is a project that's led by MIT Aeroastro. I know Dusty's been working with these folks as well to get an integrated ice-penetrating radar in this thing. So this is currently called a Stratospheric Airborne Climate Observatory System. So it has this really great acronym, SACOS. Easy to say, fun to think about. It is a solar plane, uninhabited autonomous solar plane. So it is a fixed-wing aircraft. It carries pretty much all of its weight through aerodynamic lift in the wing. The wing is covered in solar panels, has batteries, has all kinds of fun stuff on board. Now, one of the neat things about this aircraft, and one of the other aircraft that we're going to show as well, is that the aerospace folks and everybody's working on these take this integral design approach, which is to say that this aircraft is going to be designed and built for certain types of instrumentation, which is going to overcome a lot of the technical challenges that these types of aircraft that have faced in the past. So the suite of complementary missions are envisioned. The one I'm going to talk about today is considered to be a Pathfinder mission because from an engineering perspective, it's sort of the easiest mission that we can come up with that will still give us really reliable data. And all this, as I mentioned before, is being developed and led by folks at MIT Aeroastro. So that's the aerospace engineering program at MIT. The other drone that we're working on right now is a drone that's it's an autonomous hybrid airship. It's also known as a dynastat. This is basically a blimp with wings, effectively. So it's going to carry most of its weight through buoyancy. It's going to be slightly heavier than air, and it's going to fly with a wing that's connecting these two outriggers, these two helium balloons that are located on either side in black. The advantage to this is that we can pack a lot more weight on board because we can carry most of that weight through buoyancy. We make it slightly heavier than air so that the wing provides us with control, it provides us with stability, and so forth on this aircraft. Now, one of the huge advantages to this aircraft is that the goal is to design this to be a flexible aircraft that is low cost. At the end of the day, we're aiming for a price point on this thing for each individual aircraft of around $200,000 or so. So something that people can afford, something that can go to an organization like UNAVCO, so that we can basically provide a community platform to the community that you can take, that you can check out, that you can go do your own science with, and so forth. Ideally, this should be able to carry many different instruments. We'll talk about just one today that we're developing to put on this kind of thing. Now, both of these aircraft are designed to fly for months at a time. Okay, they should basically be able to fly throughout the polar summer. Right? They're going to fly in the stratosphere, which near the poles is going to be somewhere around 15 kilometers altitude or so. If you get up into the lower latitudes, stretch it up to 20 kilometers or so altitude. The goal here is to collect continuous remote sensing observations from whatever instrument it is that we put on board. So just an example mission, since we're particularly interested in WAIS, we could basically take off from one of these aircraft somewhere around the early November, and we can fly this thing all the way around, ideally, through early March, assuming that we have some ability to either store the data that we collect or to transmit it down to the ground. That's a technical challenge that we have not yet approached. But still, we get basically 4 months of operation out of this thing in terms of power and endurance and so forth, and it should operate relatively well within the winds that we would expect in the stratosphere over the areas that we're interested in observing. So the airspeed on both of these things are going to be somewhere around 20 to 25, maybe 30 meters per second. So that's about, of order 2,000 kilometers per day or so that these things can travel, right? So an example mission would be SACOS, the fixed wing aircraft, maybe 20-meter wingspan for the instruments that we want to put on board. It could launch from New Zealand, transit to Thwaites, for example. It'd take about a day to get there. It would spend more or less 4 months on station collecting data, fly back to New Zealand, land at the airport, all's well. Stratoro, that's the other one, that's the hybrid airship, the blimp with wings. That thing launches and recovers like a balloon, effectively, so it could be launched from McMurdo, it could be launched more or less in situ by whoever. Once it gets up and starts to fly, it takes over, the autonomous flight control system takes over, and it's gonna fly whatever pattern it is that users wanted. So it could be launched close to the target, basically no transit time. It could spend 100% of its time, this 4-month time, over the target. So we're by no means the first people to think to try to do this. Lots of people have worked on this problem over the years. How do you get an aircraft that flies high in the atmosphere for long periods of time? We think that, certainly my collaborators think that it may be possible to do these things now. And there are a few factors that came together to help us overcome the technical challenges of having these high altitude, long endurance aircraft. One of the things that may make this thing work out is this integrated design approach that we talked about before. So the aircraft is designed and built to support specific instruments and specific missions. So people aren't trying to build these large, kind of flimsy, lightweight aircraft to support every possible mission, which is a very difficult thing to do, but instead we're focusing in on a few missions, particularly simple missions like what I'm interested in doing, so that we can cut our teeth, we can learn what we need to do, develop the technology, and push things forward to slightly more complex missions, and so forth. So the other thing that we have going for us in terms of overcoming the technical challenges is improvements in solar panels, battery technologies. We basically get more power for less weight, and everything in this case is going to be defined by mass. So the instrument that we want to put on, and we're planning to put on, is an INSAR instrument. So there's a prototype that's been developed by Gamma Remote Sensing, and we're working closely with these folks to design an INSAR instrument that can go on these things. So the idea here is that basically what I want to do with it is to collect synthetic aperture radar observations over sort of interesting areas. These would be thwaites, these would be areas that are interesting because the processes that we're interested in studying are really well represented in these particular areas. We could fly over these areas with repeat times as sub-hourly to sub-daily temporal resolution, meter scale spatial resolution, and so forth. We get a lot of flexibility out of these platforms. We can basically define our spatial coverage versus spatial resolution and work this whole trade-off space to kind of get the data that we want over particular areas. In other words, we're happy to seed spatial coverage, global coverage, to satellites. Satellites are already doing a great job of doing this. We want to use these instruments to make very detailed observations of a few areas where we can learn a lot about the processes, about the physics that are going on in these areas. Okay? So like I mentioned before, this prototype is developed by Gamma Remote Sensing. At the moment, it is small, it is lightweight, weighs about 5 kilograms. We may be able to get that down to be slightly lighter. Again, the lighter it is, the easier it is to get on these aircraft, the easier it is to design an aircraft that flies. This particular one operates at L-band. It's about 1.25 gigahertz. If you don't know what that means for radar, don't worry about it. It's a cool frequency. It works really well. Everything's wonderful. It's great. We can trade these things around. We can go to slightly higher frequencies, lower frequencies, whatever. We have a lot of control over this because it's an aircraft. We have the ability to swap out instruments and so forth in a way that you can't do with satellites. The current version takes about 40 watts of power, which is not much. Right? That's just that's about 3 LED light bulbs or so worth of power. That's not a ton. These are the regular light bulbs you'd use in your house, not the small ones. It has an onboard inertial navigation system and it has dual GPS. It's able to maintain a particular flight pattern, stability, and so forth to collect the kind of data that we want. We are planning at the moment and hoping that we can get to a final version that's going to provide a spatial resolution of around 2 meters or so. It's going to weigh less than 5 kilograms. Going to require about 100 watts of power. It's going to have a swath width of about 20 kilometers or so. And again, it'll just sort of collect data however we want and whatever the flight pattern is. So far, this is working out really well. On a rotary drone, this drone's about 3 meters or so long to give you a sense of scale. These observations have been collected. This is just an example of observations that those folks have collected and processed over a landslide in Switzerland. So show really good line-of-sight observations to the INSAR observations, really high interferometric coherence, so low noise, in other words, with these observations. So all sort of coming together and looking promising. And once we have this kind of data, we want to be able to bring it in to some of the things that we've been working on in my group, and I know a lot of other groups are working on as well, thinking about how do we deal with spatial temporal data. How do we take these data that are collected sometimes sparsely in space, sometimes that have gaps and so forth, how do we merge these things all together to have this kind of final coherent scene? This is just an example of a paper that was published earlier this year by Bryan Riel, who's the last speaker in this segment as it is. So Cermak Kuzlek or Jakub Szalman-Izbre doing all kinds of fun things related to seasonal variations in velocity, in this case related primarily to migration of the calving front. The point here is that this is all from satellite observations. We're able to take these features, we're able to run it through some new tools that we've developed. We're able to extract different frequencies, separate things, short time scale, long time scale frequencies, and so forth. So as we get more and more data, as we get better data from drones, we'll be able to push this kind of thing even further. So look at high frequency variations from tides, again, out to sort of seasonal time scales and longer. So we'll wrap it up. Hopefully I'm, yeah, almost perfectly timed. That's amazing. Okay, so yeah, summary and conclusions. We're working toward making remote sensing observations with high spatial and temporal resolution, right? And what that really means in practice, meter scale spatial resolution, sub-hourly temporal resolution in some cases, yeah, as we see fit. So kind of, in many ways, trying to do a better job of the images on the right. Images on the right, this is all from Adrian Luckman. If you don't know his website, it's amazing, has all kinds of great GIFs like this. This is calving off of Brunt ice shelf. And this is really about the best that we can do with satellite observations, but we want to be able to do better on processes like this. We want to look at things like strain rate fields in the vicinity of the active rift tips. We want to see how these things are intensified near rift tips, how they relax away when rifts propagate, and all kinds of wonderful things that we can go on and on about later this evening if you want to talk about it. So our strategy for making these high spatial and temporal resolution observations is to develop and fly drones that can stay up in the air for months at a time. They can collect continuous observations over areas of interest that'll really help with our understanding of these various processes. We want to combine these drones with smaller, lighter instruments that are now available that allow us to make detailed and precise measurements of a few select regions, right? So we think, and this is kind of the funnest news for this whole thing, we think that it may be possible to get these things going and to start collecting data and have these things in the air kind of in a 5 to 10 year time frame or so forth, funding dependent, of course. But yeah, it's kind of a fun time. All these pieces are starting to come together. Our main primary of interest is going to be calving, but we're going to do a whole bunch of things. So anyhow, that's all I've got.
Thank you very much.
Thanks.
We're going to be able to take questions in the discussion at the end. You've been here for a couple of days now, you know how this works. So we will thank Brent, but move along to the next speaker, who is Benjamin Hills. And Benjamin's going to give us a look at some findings of ice fabric from polarimetry in Hercules Dome. And you can take it away.
Awesome, thank you. So most of the work that I've done for my PhD up to now has been focused on subglacial lake at South Pole. And I've presented that a few times in the past, but instead I wanted to present something new and a bit fresh. It's still quite preliminary, so I don't have a ton to share. But since this is kind of a session on innovative methods, I thought it would be useful to do an overview of kind of how the method, the radar polarimetry method works, and then maybe get into a bit what we have going on at Hercules Dome. Yeah. So you all will be familiar with ice penetrating radars, but typically people who don't spend every day thinking about radars will be more familiar with the measurements of travel time to get the ice geometry, or maybe the returning wave amplitude. Dusty talked a lot about power interpretations, where you could maybe interpret interface reflectivity, something like that. But this measurement is going to take advantage of phase. So if we have a phase coherent radar, we can actually take two different measurements and observe the relative phase to get at some offset. So for example, in vertical velocity profiles that are measured from PRES, you'll wait for the interface to move between time, and then you can get at that relative displacement. The polarimetry measurement is going to actually, instead of having some displacement in time, it uses the difference in wave speed based on the polarization of the wave relative to the ice crystal. So ice crystals have anisotropic permittivity, so the wave speed will travel faster if it's polarized perpendicular to the crystal or to the c-axis, and it will travel a bit slower if it's polarized parallel. And so this is useful for picking out, this specific method is useful for picking out girdle fabrics, as is shown in the stereo net there. All right, so just as a quick example, and I'll go through this kind of fast, if we have these two different polarizations lined up with and against the girdle fabric, then you'll get a phase offset between the two. And if you rotate the girdle fabric by 90 degrees so that it's now lined up with the horizontally polarized instead of the vertically polarized, then the phase shift is in the opposite direction. And you'll see that it will wrap over on itself. So obviously phase is a cyclical measurement. So you're going to get these phase wraps. And the slope of that phase shifting with depth is going to tell you something about the strength of the fabric. And you can also pick out the orientation of the fabric. If your girdle is slightly offset from the orientation of the antennas, then you're actually going to get turning of the polarization. The wave kind of turns in on itself, and you get circular, or in this case, I guess, elliptically polarized wave. Now, in the field, what we do, rather than making many of these kind of horizontally and vertically polarized measurements, we can do a set of 4 measurements with both co-polarized and cross-polarized, and that allows us to get information all around in every azimuth. So we can kind of rotate the signal and cross-compare these co-polarized coherence in order to get at the orientation of the fabric and, like I said before, the fabric strength. Now, this is Hercules Dome. So now that we know that, in theory, we can make these measurements and get at the fabric, I want to look at our field site. So for those that aren't familiar, we're doing a site selection survey at this site for a deep U.S. ice core drilling project. And it was chosen because of its proximity to West Antarctica, but it's kind of up in the bottleneck between East and West Antarctica. So hopefully Eemian ice is preserved in this area. In this map that I show, you can see some of the surveying that we've done so far, both kind of deep surveying, deep radar, some shallow radar for accumulation, as well as these PRS measurements, including polarimetry shown in red. And so we've made several polarimetry measurements, kind of a transect from west to east along the divide there and through the saddle, as well as one transect going north-south within the saddle itself. So some of the questions that I'm interested in answering with these polarimetry measurements is kind of what is the flow history at Hercules Dome? If we can get at the fabric, we can potentially constrain history of flow, as well as does the fabric show signs of stability or lack thereof? And that can hopefully tell us about whether Eemian ice has been preserved in this area, as well, along with some other analysis that other folks are doing with the other data sets. So just as a quick look at the data that we have so far, this is from the Hercules Dome saddle, so kind of in the center of the saddle there. And what I've done is I've aligned it with kind of the azimuthal direction, so north, east, and west there, and on the left is the polarimetric interferogram. And the green line shows the direction of the fabric orientation, so that's the direction of the girdle. So in this case, it's actually east-west girdle. And then in the right panel there, you can see the relative phase shift between the HH and the VV polarization. And the signal is pretty flat, kind of near the surface. So what that tells us is that there's not a strong girdle. It's likely either mostly isotropic or that you have a single pole fabric. And then kind of in the middle, you have this slope that you can see, and that tells us that there's likely a girdle fabric there. And then kind of closer to the bottom, we lose that signal, and that's because we lose phase coherency for those deeper reflections. Okay, now moving over to the eastern side. So again, we kind of have this ridge running from west to east, and then there's also kind of a north-south ridge on the east side here. So we divide the dome up into west dome, east dome, and south dome. And this is kind of on the east side where ice is beginning to flow a bit east-west, and the flow dynamics are a bit more complicated over here. But we can see that the slope of the phase shift is actually in the opposite direction. So we have a 90-degree fabric rotation here. So this is kind of the trend that we're starting to observe. Okay, as an overview of the data that we've had, and I haven't shown everything just because there's not quite enough time, but kind of running along the east-west ridge, we tend to see this east-west girdle, which makes sense with north-south extension. So the crystals should rotate, they should rotate away from the axis of compression and towards extension. And then on the east side, we have the 9-degree rotation, like I said, and then kind of into this armpit area is what we're calling it. The signal gets a lot more confusing, and there's not quite as strong of a girdle. Looking forward to the upcoming season, I want to make a few more measurements in terms of the polarimetric survey, as well as kind of constrain these polarimetry data with both vertical strain rates. We need to do some repeat AP-res measurements, as well as the surface strain rates, and that should allow us to kind of interpret the polarimetry data in the context of how the ice is moving today. I also wanted to just do a quick shout out to a collaboration that we're kind of starting with some of the folks at BASS who are designing a new PRES system, lower frequency in the HF spectrum, 20 to 40 megahertz. And the idea with this is that hopefully we can get some phase coherence in those deeper layers. So I'm going to try to do some polarimetric measurements with that, as well as they want to do some just like surveying, some profiling with that as well. Thank you.
That was really great, and I'm reminded that I should have pointed out that Benjamin is a student, so if you are taking in the impressions that you had from that presentation and want to give some feedback, that would be a great thing to do. Anna is also a student and is coming up and is going to tell us about some new radar systems that will let us look inside the ice, under the ice, show us everything we ever wanted to know. Yeah, thank you. No
there
peeking.
we go. Great. Thanks for having me here today, everyone. My name's Anna Broome. I'm a PhD student in electrical engineering at Stanford University, working with Dusty Schroeder and the Stanford Radioglaciology Lab to develop a new multi-frequency ice-penetrating radar system that we think will help us better characterize end-glacial and subglacial conditions of ice sheets. So ice-penetrating radar systems have been used since the 1960s to study the polar ice sheets. They're often flown on airplanes or towed behind snowmobiles, and they are really useful for characterizing the different subglacial and end-glacial properties. So quantitatively, we can describe the process using the radar equation, shown here in dB, where the received power is a function of system parameters such as your transmit power of your radar and antenna gains, geometric spreading, which describes how the signal propagates through medium and 3D, birefringence, which is the effect that crystal orientation fabric has on rotating the polarization of the signal, attenuation, which describes energy lost as the signal propagates through the ice column, and then basal conditions, which will be your basal reflectivity and roughness of the bed interface. So that's a lot of variables that go into one equation and one measurement, and that results in a lot of ambiguity in a single measurement. So we can only correct for system parameters and geometric spreading, which leaves us with birefringence, attenuation, and basal conditions that could tell us a lot about the ice and some really helpful properties, but are right now creating ambiguity in our measurements and their interpretations. And I want to mention that there are ways around this ambiguity that people use today, such as large-scale empirical analyses, as well as comparing relative as opposed to a long track or as opposed to absolute changes in the power. But the question I'm trying to answer is, if we had an instrument that could accurately measure and correct for all of these effects, not just one, what would that look like? And so right off the bat, I want to say that we can correct for birefringence. The talk Ben gave just before me is a great way to do that. If you have a system that has quad polarization or the ability to collect quad polarization data, we can do that. So let's take birefringence out of the equation, and now all we've got to deal with is attenuation and the basal conditions. So I'll start by showing you what basal conditions can do to your radar return if you don't correct for them. So right here I'm modeling a single frequency, relatively narrow band radar system. The black dot is the true forward model parameters for the excuse me, basal conditions, so the roughness and the reflectivity. And that black dot causes a certain power loss in your received power. This black dashed line, I call it an ISO loss curve, and that represents all of the parameter combinations that could produce the same effect in your received signal as those conditions at the black dot. But we've also got to take into account the inherent uncertainty in our measurement. So that's plus or minus 3 dB in this example, and so we expand our black dashed line into the shaded purple region. And every combination of parameters in that purple region could cause you the same signal, or could cause the same effect in your signal. So the key takeaway here is that while your true basal conditions might be water with some overlying moderate roughness, it'd be totally reasonable to make an interpretation with just this data that you're looking at really smooth frozen bedrock. So that's a massive ambiguity, and the question is, how do we deal with it? We're proposing to use a multi-frequency radar system. So by exploiting the frequency dependence of roughness vis-a-vis the frequency independence of material reflectivity, we can separate those two signals and start to characterize the basal conditions much better. So what you can see is on the right, when we have 3 different curves, sorry, I should explain these again. So the black dot in these conditions is again showing the forward model parameters, and in this case, the red regions show the overlap area for the multi-frequency system or the possible space of measurement parameters. And so you can see that when you've got the multi-frequency system with its 3 curves overlapping, we're getting a much smaller possible range of parameters, and that's great. That is going to allow us to make much better interpretations. And so we've got a multi-frequency system with frequencies spanned by orders of magnitude, and to even get better data, we can improve the radiometric resolution of our system, which is that inherent uncertainty in our measurement. So we do this by building in internal calibrations, making better external calibrations. So moving from left to right, we're reducing the uncertainty in our system, so that decreases that shaded area, which in turn will decrease the overlapping area. And so you can see, it's a little hard to see, I guess, but the red area goes from some moderately sized thing to some very finite, small parameter space, so that's great. And we believe that this will allow us to comment on things like the porosity and saturation of subglacial materials, not just sort of the level of, is the bed frozen or is it thawed? So now I want to walk through a little example. If you imagine that we're collecting a radar line over these subglacial conditions, so going from rough, cold rock over a subglacial lake and then back again over rough, cold rock. When we go over this lake, or over these conditions, our received power at any given frequency is going to go from lower over the rough rock to higher over the mirror-like lake reflection, and then back to lower again over the rock. And so at each point, we can break down that signal with our multi-frequency system into those ISO loss curves that I showed earlier. This time, the overlap area is shown by these little circles on the screen. And when we plot those along track changes, we can see that the reflectivity, which is the bottom signal here, increases over the lake, as you would expect, and the roughness signal decreases over the lake as well. And so if we know attenuation, or we can correct for the attenuation in the signal, we are able to pull out specific bed material change or properties and roughness values. But even in a case where attenuation is unknown or can't be corrected for, we can still say really crucial things with our multi-frequency system. So attenuation is a frequency-independent effect at the frequencies we use, which means that it causes a constant offset in our signal, sort of an effective reflectivity, if you will. And so you can see it decreasing the shape here, but if we assume that attenuation is relatively unchanged along the horizontal length scales of interest, then the shape of the signal will still be preserved, and we can make relative along track changes, or we can make interpretations of relative along track changes, so you would still be able to attribute these changes to a change in basal material or thermal state. But if we really want to make absolute measurements, we do want to be able to correct for attenuation. And so the way we're proposing to do that is by integrating a radiometer into our system. And a radiometer is a passive instrument that measures the thermal emission of a target. In our case, our target is the ice sheet, and we'll be measuring thermal emission from the basal material as well as internal emission from within the ice. And so, this radiation is strongly dependent on the physical temperature of the ice, as is the attenuation that a radar signal experiences. But the issue is that the attenuation of the radar signal and the thermal emission that the radiometer measures are sensitive to physical temperature in different vertical portions of the ice column. So as you can see on the right here, we've got the HF and VHF radar is sensitive to much deeper ice, where the radiometer is sensitive to more of the upper to middle portion of the ice column. So we really believe that by combining these two instruments into a tightly integrated single system, we'll be able to measure top to bottom temperature and correct for attenuation in our surveys. And so I want to give you a little preview of what the system will look like in deployment. It'll be on a sled towed by a snowmobile. We'll have antennas, a quad pole on the front to correct for that birefringence, and a resistively loaded dipole trailed behind. So just to conclude, if we design and build this radiometrically precise system, we think it's got a wide range of use in many applications, not just correcting for basal roughness, as well as studying in glacial temperature, but things like ice shelf roughness, studying marine or dirty ice, subglacial and end-glacial hydrology, and definitely looking for opportunities to test and discuss other applications of the system. So if you're interested, looking forward to chatting later. Thank you.
Thank you very much. It looks like an amazing system, and I think there will be a lot of people who have things that they want to learn from something like that. Now we're going to go to Marion Mckenzie, who is also a student, so be attentive. And we're going to take a whole new way of looking at the bed of the ice sheet by getting the ice sheet out of the way, right?
Exactly.
So do you have everything you need there?
I think so.
Marion Mckenzie.
Thank you. All right, so I'm going to spice things up, and we're going to talk about subglacial geomorphology in the Northern Hemisphere, but I want to preface this by saying that this can be extrapolated because it is process-based to thinking about how we can map these bed forms in Antarctica. But I'm Marion Mckenzie. I'm a PhD candidate at the University of Virginia studying with Dr. Lauren Simpkins, and this work is also in conjunction with Dr. Sarah Principato at Gettysburg College. So we know that streamlined subglacial bed forms can tell us about the direction and speed of ice flow. They can be both erosive and depositional in nature, and they can be used to map and understand previously glaciated landscapes. They occur on a wide range of scales, so they can be centimeters long, such as in the case of glacial striations in the bed. Whalebacks can be meters long, so these are both erosive features. But then you can have really large depositional features that can show up in digital elevation models as well, such as megascale glacial lineations, which can be up to kilometers long, and flutes, which are smaller versions of depositional streamlined bed forms. Qualitatively, these bed forms are associated with streaming ice flow, like I mentioned, and that is possible due to looking at their morphologies. And so if you look at the length to width ratio, the higher that ratio is, the faster we know that ice was flowing. But these parameters can also be associated with bed properties, the presence of meltwater in previously glaciated regions, as well as the potential for a system to erode or deposit sediment on the surface. And so these contemporary streamlined bed forms are indistinguishable between those on paleo-subglacial beds. And so that is why we can use them as proxies to understand how ice sheets interacted with different types of bed topography and lithology in these previously glaciated landscapes. And so while we know that bed properties can have opposing effects and varying degrees of influence on ice stream behavior, and we know that these bed form morphologies are really helpful in understanding how the ice sheet interacts with different types of beds, large quantitative assessments are lacking, and so this is what this work aims to fill in that gap. And so in this work, I look at streamlined bed forms in deglaciated landscapes to understand how ice would have interacted with different types of bed lithologies and topography. First, I'll identify streamlined bed forms across a range of deglaciated landscapes. I will then correlate bed form metrics with landscape variations. And lastly, I infer ice flow dynamics of ice streams across a variety of landscapes. So I have 9 sites across the deglaciated northern hemisphere. 3 are in the United States, 3 are in Canada, 1 is in Iceland, 1 is in northern Norway, and 1 is in northern Sweden. And there are a variety of different bed types and topographies across these sites. And so the Puget Lowland in the upper left-hand corner is an unlithified sedimentary bed with crystalline bedrock highs. We have several sites with lithified sedimentary bed surfaces, and still more with crystalline and volcanic bedrock. I put these 2 in the same category because both of these bed types are resistant to water infiltration into the subsurface. Sites indicated by stars are topographically unconstrained, while sites that don't have stars are in valley regions, so they are topographically influenced. And so I used a process called Topographic Position Index to characterize these bed forms. This system looks at slope variations across digital elevation models, and by doing that, we can pull out different features in the landscape. And so this is an example of one of the sites. This is in Chautauqua, New York. When implementing Topographic Position Index, it pulls out all positive slope variations, and this is what the output looks like. It pulls out these polygons that are in black. And from here, some were incorrectly identified and others were missed, and so I manually went through each of these sites and fixed them. And so this is what the final product for this site looks like, but for all of the sites, over 7,000 bed forms were correctly identified by Topographic Position Index, while nearly 4,000 were manually mapped. So in total, I mapped 11,628 bed forms across these 9 sites. All of the bed forms are shown on their sites on the right, and the colored boxes will be shown in the next slide. They will be where we look at spatial distribution of those elongation ratios. Taking a closer look, we can see that each of the sites has a wide range of bed form sizes, as well as directions, orientations, so they're all pretty diverse. These features are all also erosive and depositional in nature. We didn't differentiate between the 2. And so when we look at the morphologies between bed form width on the x-axis and bed form length on the y-axis, there was a trend that appeared where we see that there is a minimum threshold in which bed forms must reach in their length and width in order to be identified by this mapping system. And so we can see that all bed forms, regardless of the bed that they were created on, have that same threshold. And so we can infer that streaming affects the bed similarly, regardless of the type of bed it is on. Similarly, if we look at the elongation ratio, which is again a measure of the length to the width, the distribution of that across each site, they are remarkably similar. And so it clusters around an elongation ratio of 5, but then there are positive peaks where some regions are moving faster than others. And if we look at this spatially, so these are the boxes from the last slide, we see that in a lot of these areas, streamlined bed forms are more elongate in the center of ice streams, indicating that there may be some influence of lateral drag on the outside, which would indicate that ice is able to move more faster and create more elongate bed forms near the center. When we look at the surface elevation distribution of the bed forms, we can see that in areas that have more elongate bed forms, also associated with faster flowing ice, there is more even distribution of erosive and depositional processes in the subglacial environment, inferred to be more organized subglacial flow. Whereas when we have more slow flow or less organized flow indicated by lower elongation ratios, there is a greater range of the elevation of the surface, meaning that there's more chaotic flow and it's not able to organize itself to deposit sediment or erode the surface more evenly. When we look at each of the sites, specifically at their lithologies and topographies, On the left, we have that elevation range, which is looking at the surface elevation of each of the bed forms. The biggest ranges occur in sites that are topographically constrained and have malleable beds, such as in the case of the volcanic bedrock in Barðardalur, Iceland, and the unlithified sediment of the Puget lowland. And so this would mean that these sites induce more chaotic flow and less organization in the subglacial environment, whereas at sites that have lithified sedimentary beds, they and are not topographically constrained, they have even erosive or depositional processes along the surface, indicating that this would support more persistent or organized subglacial flow. On the right, we have our elongation ratios organized by site, and we can see that where you have topographically constrained regions, you have more elongate bed forms, which is also associated with faster flowing ice. This could be due to a funneling effect, where as ice enters into a topographically constrained region, it becomes thicker, induces more frictional heat, which causes more meltwater, which would increase the ice speed. But then there doesn't appear to be any association between lithology or elongation ratio, which also indicates to us that there is some correlation between, there's a higher order control of topography on elongation ratio of bed forms and therefore ice speed than lithology does. And so in conclusion, we see that TPI works best on bed forms within a specific elongation threshold where highly elongate flute-like features may not be identified and need to be identified manually. I suggest that working in machine learning and using the highest DEM resolution possible will improve the use of TPI. Consistencies in streamlined bed form morphology indicate similarities in processes of the bed regardless of the bed type it is occurring on. Unconstrained lithified sedimentary beds support landforms with less surface variation, therefore consistent ice bed interactions, while constrained regions promote more variable landforms and more chaotic ice flow pathways. And lastly, we see that constrained sites produce more elongate features, likely due to increased ice thickness and greater ice streaming, and there's also that first order control of topography on ice stream speed. I would like to thank Dr. Lauren Simpkins and the Ice and Ocean Group for their support, as well as my data sources. And the University of Virginia is in the traditional territory of the Monacan people, and the Algonkian Regional Park is in the traditional territory of the Manahoic peoples. And I would like to acknowledge the tribal governments and their roles today in taking care of these lands. And I'm happy to take questions during the discussion.
Okay, that so far has been a great set of talks, and the final talk in this session is a remotely presented one. So we'll just get that queued up now. And it will be Bryan Riel.
Hello, everyone.
About calibrating flow law. Is he talking already?
Whenever you're ready.
Go ahead.
Thanks for inviting us to present at the WAIS 2021 workshop. My name is Bryan Riel, and I'm a research scientist at MIT EAPS, working with Brent Minchew. And today I'll be sharing with you our work on calibrating flow law parameters and uncertainties over Antarctic ice shelves with physics-informed neural networks. So, jumping straight into it, as the title implies, our main objective in this work is to calibrate the parameters in Glenn's flow law from observations of ice sheet motion. So while calibration of these parameters has been performed in a laboratory setting, as shown here in the earlier works by Jessica et al. And Goldsby and Kolstad for estimating the exponent n, the availability of remote sensing data has made observational calibration a much easier task. So as a recent example, work by Joanna Milstein and others, which will also be presented at this workshop, has also looked at strain rate fields over ice shelves within an extensional regime. And they're able to provide fairly robust estimates of the exponent with mean values of roughly n is equal to 4. For the prefactor, estimating its spatial variation from remote sensing data has been done for the past 2 decades now, where we assume a constant value of n. And these studies have shown the overall importance of shear weakening and heterogeneity of ice stiffness over ice shelves, which has important implications for modern glacier and ice sheet response to changing stress conditions. I'll note that in this figure, they parameterized the prefactor as b is equal to a to the negative 1 over n for numerical purposes, which we'll also be doing for the rest of this talk. So our main goals in this project are: 1, we want to extend the analysis of the flow law parameter estimation, where we'll mainly focus on the prefactor, to more complex flow regimes using remote sensing data. And two, we want to develop efficient methods for uncertainty quantification for those flow law parameters. Here, as is done in many previous studies, we'll focus our analysis on ice shelves, mainly due to their favorable geometry, their thin relative to their spatial extent, and the fact that they experience negligible drag at their base. So these conditions allow us to apply the 2D shallow shelf approximation with confidence and assume that the strain rate at the surface is constant for all ice depths. As I mentioned before, there's a long history of estimating flow law parameters, and primarily the prefactor, from surface observations for the largest ice shelves. Importantly, the vast majority of these studies have used optimization-based techniques, which we usually refer to as control methods. So while classical inverse and control methods provide us with parameter values that best fit the data, it's also important to accurately quantify uncertainties associated with those parameters, primarily because realistic uncertainties are crucial for probabilistic forecasting of ice sheet evolution. Luckily, there's a tried and true probabilistic framework for this using Bayes' theorem, which states that the posterior probability distribution for model parameters is proportional to the product of the data likelihood distribution, or goodness of fit, and a prior probability distribution, which encodes what we expect the range of parameter values to be without having seen any data. Now, the central challenge in using this framework is sampling or modeling this posterior distribution, where standard Markov chain Monte Carlo methods, or MCMC methods, can be quite prohibitive for a large number of parameters. So in this work, we wanted to explore an alternative to sampling, where we instead parameterize an expressive surrogate or approximate distribution that has its own set of trainable parameters. So the goal then for Bayesian inference is to optimize instead of sampling. We want to optimize a surrogate distribution such that it best matches or approximates the true posterior. And the most commonly used metric for this is the KL divergence, which we then need to minimize. Now, this optimization approach, called variational inference, has recently increased in popularity due to use of deep neural networks, which have been shown to be suitable for representing complex nonlinear transformations of data. And in this work, we'll use what's called a mean field approximation surrogate, which represents each model parameter as a random variable with a mean and a standard deviation. And we'll see in a moment the main limitation of this approximation. So while variational inference itself can provide a boost in computational efficiency over MCMC methods, we take things a step further by modeling all high-dimensional spatial fields, including observations and model parameters, with neural networks. So instead of having a discretized mesh for an ice shelf, we construct neural networks to take in spatial coordinates as inputs and spit out surface variables as outputs. To train these networks, we then need to construct a loss function that combines information from data with information from physical model, which is nothing new and is exactly what inverse methods do. So we're just rearranging things in a way that is suitable for network training. So to put everything together, let's look at this diagram of our training procedure. We create two neural networks. One is in charge of reconstructing surface observations, and one is in charge of reconstructing the statistics of the rheology parameters. So for a single data example, we input spatial coordinates to both networks. The first one predicts thickness and velocity at the surface, and we measure the misfit between those predictions and surface observations in order to compute a data loss. The second network predicts a mean and a standard deviation for the flow law prefactor, which we then combine with the thickness and velocity predictions in order to compute the force balance with the shallow shelf approximation in order to measure the residual force balance between the driving stress and the resisting membrane stresses, which we expect to be zero. Now, the final component of the loss function is a KL divergence between our mean field surrogate and the prior, which serves as an additional regularization on the neural network prediction. So these two components form the physics-informed neural network component of this whole framework, and we combine everything into a combined variational loss function for the posterior distribution for those rheology parameters. So to concretize these concepts, let's look at results for a synthetic 1D ice shelf. I've simulated a laterally confined ice shelf where lateral drag is parameterized such that the momentum balance is purely 1D. And I've specified a stress exponent of n is equal to 3, and I've created a prefactor field that varies sinusoidally in space. So after simulating the ice shelf for about 200 years, we'll then use the noise-free velocity and ice thickness profiles to train both of our neural networks to try to predict the B field with realistic uncertainties using the mean field approximation. As a baseline, we'll use MCMC to sample the true posterior, And I consider MCMC to provide us the gold standard results for comparing our variational inference. And for the MCMC case, we'll discretize the 1D field into 200 elements and use finite differences to compute the momentum balance. Now, the first thing that we can see is that the mean predictions shown in orange for both methods are very close to the true sinusoidal B field, which is shown in blue. And the second thing we can notice is that both methods produce spatially varying uncertainties, where they both indicate the uncertainties increase as we move closer to the ice front. And in this simple example, it takes about 4 to 5 minutes to get 2,000 samples from MCMC and 1 to 2 minutes to train the neural networks for variational inference. And we do expect much larger efficiency gains as the number of parameters increases. So while this is a good start, we need to check if uncertainties from location to location are correlated with each other, which we can do by looking at the joint distributions. So here I'm showing joint marginal distributions for 3 locations, 40, 14, and 6 kilometers upstream of the ice front. And samples from the mean field surrogate are shown in blue, while samples from MCMC are shown in orange. And we can see that at the point 40 kilometers upstream, it's far enough away from the other 2 points that the samples are essentially uncorrelated with samples from the other 2 points. However, when the points are closer together, which is the case for 14 and 16, for the 14 and 16 kilometer points, MCMC shows very strong covariances here, which the mean field surrogate is not able to reproduce. And it's important to emphasize that for most glaciological inverse problems, we do expect non-zero covariance for parameters that are close to each other. So in order to accurately capture these covariances, we'll need to use higher fidelity approximations. So finally, let's look at some results for a real-world ice shelf. So we'll apply our variational inference methods to velocity and topography data for Rutherford ice stream in Antarctica. We'll use a secular velocity field derived from Cosmos SkyMed SAR data, and we'll use bed machine for the ice thickness data. And we'll also fix a stress exponent to n is equal to 4. Now, after applying variational inference, the leftmost map shows the mean log prefactor, log B, where cooler colors correspond to colder and stiffer ice, and warmer colors correspond to warmer and softer ice. And the middle map will show uncertainties for the prefactor. Now, the thing I want to emphasize here is that having both the mean and the uncertainty for the parameter field can open up some interesting analysis. For example, we can compare our results to a map of ice thickness on the right, and we can see that the thicker parts of the ice shelf correspond to the stiffest or coldest ice. On the other hand, the areas with these inferred softer ice seem to be co-located with fine scale morphological features, which could themselves be surface expressions of pinning points or ice rumples. So interestingly enough, the largest uncertainties are also located in these areas, which could be some kind of clue on the limitations of either oversmoothing or the limitations of our SSA model approximations for these locations. So overall, having realistic uncertainties can open up a more thorough assessment of our physics and our data. So speaking of flow law parameters, we've only discussed the prefactor so far, but we're also working on methods to estimate the 2D stress exponent n for 2D flow using time-dependent data. And we're also looking to integrate observation errors into the probabilistic framework and investigate other variational inference approximations for modeling parameter covariances. So with that, I'll conclude this presentation, and I look forward to discussing this work with you all during the live session. Thanks.
Thank you to all of the speakers from this session. Bryan is present online, I think, so we can, I think we can make him be a giant head behind us. And if I could invite the in-person speakers to come up to the front, so you'll get to question each other or chat amongst yourselves, or if there are people in the audience who have questions, you can line up at the microphone here. We're also encouraging the people online to write their questions into the chat. If I can figure out how to find questions in the chat, can you manage the chat questions? Thank you. And so I'll take a question from Dusty.
I have a question about the ice fabric. So you say you're going back and going to make more measurements this year. Our other student, Nicole, who's not here, has been working on bistatic systems, not for polarimetry primarily, but you can rotate them too and get off-axis elements. do you think from what you've seen so far that there's significant off-axis fabric, or do you think it's mostly vertical?
Yeah, great question. I'm super interested. We should talk more about maybe, if not this year, the nice thing about these polarimetry measurements is that you can do them in one season. Yeah, so a part of the question is that for these measurements that we're making, the fabric has to be kind of oriented, or the crystals, the anisotropy has to be in this XY direction, because you're just, the wave is propagating directly down. But if you move the antennas apart, then you can actually get at anisotropy in other directions too. So yeah, we should talk about that. I think that there probably is some other signal outside of just this kind of girdle that we've been observing, especially kind of down in the grid southwest, where we have the dome wrapping around here. The dynamics are quite complicated in that region, so it'd be interesting to see if there's any other fabric signal down there.
Cool, sounds good, we'll follow up.
Yeah. Sorry.
Really interesting talks, everyone. So my question's for Marion. So you were looking with these paleo ice stream lineations that you assume some velocity field there, but how do you account for dynamic changes in width of the ice stream during its evolution? Or conversely, could you use the field data to invert for some sort of history of how the width has evolved through time?
That's a good question. As far as width, I really only took like snapshots of where there were clusters of lineations, so they happen in swarms. And so I'd find where there were swarms and then kind of just like look at those specific areas. As far as being able to tell how it changes through time, I did notice that at some of the sites there were multiple very clear directions of lineations, which would indicate that at another time there would have been another advance at a different direction and the other lineations were overridden. So there is evidence of that, but as far as like mapping it through time, I think unless there's fieldwork involved or any sort of like on the ground analysis, I don't necessarily think that would be possible.
Yeah, I can unmute myself and ask. Yeah, my question's for Bryan. Bryan, is there any notion of like an information criterion that is incorporated in sort of the neural network such that you could do model selection basically in this process, right? So let's say you wanted to apply this to the problem of understanding basal friction, but you don't know what the model should look like, right? What the formula for basal friction should be. Is there sort of a way to basically select in between sort of different dependencies on different variables?
Yeah, you could, since you're essentially formulating the problem as a Bayesian problem, there tends to be a there's some history in doing model selection by looking at your posterior distribution with regards to what you expect it to be with your prior. So having your prior is already a form of saying, of kind of encoding what you expect the kind of complexity your model should have. And then the posterior itself will then tell you, okay, how much information did I extract from the data? If you extracted a lot of information from the data, then you're quite far from your prior. And that way, that could be a penalizing factor. So in short, essentially, by having the posterior distribution, you can actually do pretty formal model selection that way. It really just all boils down to the complexity of the spatial variation that you're getting in your, let's say, your basal drag, which will be controlled by the prior in this case. And in this prior, you can actually enforce things like spatial correlation, or if you don't know anything about spatial correlation, then you can have them be completely independent. But all those things can be baked in to the Bayesian framework in a way that these things can be formalized.
My question is for Brent. So with your very cool-looking solar-powered plane, as a meteorologist, I was curious if there's any meteorological applications of the plane, perhaps in the future, as if like maybe you could attach a microwave sensor or something that could probe clouds. I think some weather people could be quite interested in this concept, perhaps.
Yeah, for sure. That's one of the planned missions for this kind of thing. So, Carrie Emanuel at MIT is leading a study on that and trying to understand how these planes can best be used to, for example, track hurricanes, measure wind speeds within the eye walls of hurricanes, and so forth, using lightweight onboard radar as well as thermal cameras and so forth. So, loads of applications. In addition to that, there's some folks that are interested in free radicals that are transported into the stratosphere from thunderstorms and things of this nature. So a whole host of missions that can be performed with these types of aircraft. So, cool. Sky's the limit, so to speak. Tell a corny joke. Yeah, I couldn't help myself.
So my question is for Anna. With respect to these multi-frequency radar, like how well would you expect it to be able to resolve like debris-rich layers of basal ice? And if that's possible, what would be kind of like the expected like lower limit as far as like layer thickness that you would be able to hope to?
Yeah, that's a great question. Thank you. So I think that you can definitely resolve debris-rich layers of basal ice, and as well as like marine ice or basal freeze-on that has a different sort of salt content. In terms of the layer thickness, that's going to be pretty dependent on the bandwidth that you use at each frequency to sort of dictate sort of what your vertical range resolution is. So at the lowest frequencies that I'm talking about, right, like 2 megahertz center frequency, there's not that much bandwidth that we can realistically get. But if we've got one channel at like 300 megahertz that should be able to have, at least 20 to 30% fractional bandwidth, which would give you a range resolution less than 1 meter. So if that is an application that you're interested in, the system could be adapted to be much more optimized for that, which is one of the beauties of like building it on a reconfigurable platform.
That's pretty cool. As a quick follow-up, you mentioned being able to like resolve porosity within a till column. What's kind of like the theoretical like sensitivity to porosity that you might hope to pick up on?
Yeah, that's a great question. I don't have like a super definite answer for you. It depends on sort of what mixture model you're willing to use, which is again something that is rather unknown. But off like the back of my head, I would say, probably changes of like 20%.
Oh, cool. Thank you so much.
So, question for Marion. In thinking about your bed forms, what are your thoughts very generally on assessing when the bed forms formed within the glacial cycle, advance, retreat, re-advance, and so forth, and particularly how are you going to link your paleo and present features that you're looking at from DEMs to what we can actually glean from current subglacial features?
Yeah, so that's the question, right? Like I feel like there are a lot of theories out there for how they form, and it's not completely settled which one is correct. My perspective is that they occur during ice advance, and it's part of that abrasion and erosion cycle for the erosive ones, and then deposition also occurring during advance. The mechanisms in which that occurs, I would recommend a paper, King et al. 2009, Shaw et al. 2003. Those are just a few examples of theories.
Dougal asked the first question I was going to ask, but kind of as a follow-up, throwing it to Ben and maybe Anna. can you do anything with Fabric to get at what, you know, this basal package looks like? And what could you do in a polarimetry sense with an instrument like ANA's?
Yeah, good question. And I might turn it over to Anna because I think that she'll be more able to give details. But I think it's important to, in some studies that we've seen, for example, T.J. Young just published a paper where they're kind of getting at Fabric a bit, using just kind of like a conventional survey without the full quad pole. But I think if we're going to constrain the birefringent losses very well, we should really actually get at these more sophisticated systems that are doing the full quad pole measurement. Yeah.
Yeah, so in terms of polarimetry with the system I described, we're putting in quad polarization antennas. So instead of doing sort of the rotational stuff that Ben talked about, you can just collect that data from one system. So I think my goal is to enable all of these polarimetry techniques with the data collection that you can do on a snowmobile towed ground-based system.
Yeah, thank you. This is so low, sorry. I have more of a comment than a question, really. This morning we heard about ice shelf or ice sheet instabilities a lot. And this afternoon we heard about new measurement concepts. And I had a little bit the feeling that this morning and this afternoon was the linkage between measurement needs and potential measurements could be or maybe should be made stronger. You know, and I would love to hear at one point from the community, you know, forget about technology, what's possible, what's not possible, but what do we need? What are the critical measurements that would advance our understanding of, you know, the instabilities that we have been discussing this morning? You know, the decadal survey talked about ice elevation, and I'm not sure whether this is the best, actually the most urgent measurement need, you know, and we had a brainstorm meeting at HQ at one point, and about what measurements were forgotten in the decadal survey. And my comment was, just to throw something in for cryo, ice vertical structure. I'm not really sure what that means. I mean, I know I have something in my mind, obviously. But what that means in terms of spatial resolution, vertical resolution, penetration, etc. And, you know, these measurement concepts, I mean, I love it, right? I'm you know, all for UASs, and everyone knows that, and you know, new measurements concepts. But I think the linkage needs to be made better. What do we actually and quantitatively need to advance our understanding of, you know, ice sheet instabilities as discussed this morning? And at one point, I don't know, hopefully soon at one point, I would like to get a group together and actually come up with something, with a roadmap for what measurements do we need to advance, you know, our field. Yeah, this was just a comment and observation. Thanks.
Is this separate from what the NASA SDC is already doing? Thorsten, that's a question. This is separate from what the NASA SDC is already doing by defining all these mission requirements and measurement requirements and resolutions and timescales and so forth, or is this is something separate from that, or what are you asking for, I guess?
So yeah, that's a good point. So the decadal survey incubation thing, the title is Surface Topography and Vegetation. And right there is a limitation, right, that I think is still limiting personally, because it says surface topography, and that's where the ice sheets come in. If we can make a good case that it's, you know, something beyond surface topography that we need, you know, then we can make a case and can, you know, and we can be quantitative in justifying it. Then we can make a case that, you know, let me just say it frankly, you know, like a LiDAR is not a solution. Yeah, it does surface topography, but the community needs something different. In addition to topography, we need, you know, accumulation layers. We need to know whether the base is, you know, melting or freeze, not melting. We need to know the bedrock topography even better, what, you know, a bed map can provide at this point. And, you know, if so, what is it? Where do we need it better? Yeah. So I think STV, the Decadal Survey incubation, may again be with surface topography, not addressing, and I'm asking you now, our most urgent need. Is surface topography the most urgent need, or is it bedrock topography, or is it accumulation layers, or is it ice shelf, short-term thickness changes? You know, we talked about this, or I've heard about this this morning as well. Does it make sense? I'm rambling a little bit.
Yeah, I guess I was just curious. I mean, there are a few working groups. You know, Ala Kazandar is leading one of these on, I think he's leading the one on ice penetrating radar, and Alex Gardner is leading one on surface velocity observations. And I was curious as to what it is, what are you asking for that is not already being done by these existing standing committees?
Yes. All right, so we can have a chat.
Yep, wonderful.
It's a good
Yep.
point. Sorry, I just don't want to. Okay.
Since I'm holding, I'll just say my dream one would be time-dependent strain rate observations, particularly near rift tips and things of this nature where fracturing is taking place and so forth, so we can understand intensification of stresses and what's driving rifting, fracturing, and potentially things like ice cliff instability and so forth.
Yeah, it'd be great, I guess, for me if someone wanted to do more laboratory dielectric measurements of ice at the frequencies I use.
Mine's pretty unrelated, but I would say pretty high resolution digital elevation models, which there already are a lot of. It's just a matter of finding them.
Yeah, I think that in some of the talks that we've seen today and yesterday, it's apparent that we still haven't fully constrained ice rheology. I mean, n equals 4, n equals 3, and I think basal processes are still quite unconstrained as well. So I think that as we can kind of scale up these methods, in particular, I guess I'm interested in ice penetrating radar methods where we can start interpreting power and phase information a bit more. And with instruments like Anna's, I think we can do that in a more sophisticated way. Hopefully we can learn about both the ice rheology and the basal properties and constrain ice dynamics a bit more.
I'll speak for Richard Alley, who seconds Brent's point for the time-dependent strain rate and damage observations, and to thank the speakers for their great work. Does Helen want to speak for herself or type something?
Yeah, I can. It's a bit weird doing this remotely and being so huge on your screen. Yeah, I mean, I really like what Torsten said, and as a member of the steering committee for the previous decadal survey, I have to say it was really frustrating to experience kind of the lack of engagement, I guess, from, I mean, this community could have got a lot more involved. So we need to get ready. And I think Torsten's absolutely right that now is the time. I mean, the next decadal will be coming up in probably, I think it would be 2025 when it'll all start ramping up again. And so we need to start thinking now about what it is like, what missions are actually ready to fly on space. I mean, Dusty, and we heard loads of talks today about how technology may or may not be ready, but we need to think about what could be ready in the coming decade. I will say that the timing of the past decadal was terrible for ice altimetry in particular, because of the timing in terms of it was right before ISAT-2 was launched, so that we didn't know whether it was going to be any use. So we just need to be a bit strategic and organize ourselves as a community, because I will also say that the voices from other people in earth sciences and other communities are much more, they're louder, they're more coordinated, they've got their acts together. So I think Torsten's spot on. We definitely need community to really sort of organize and figure out what measurements it is that we need for the next decade. And not wait until it's all, you know, put in place. Let's not get caught out like we were last time.
Okay, well, thank you, Helen. Thank you, Torsten, for your questions. And thank you very much to the speakers from this afternoon's session. I think if we can give them one more round of applause, then Matt will have some announcements.